Now in this lecture we'll answer two questions. In the first question we find out the area of this trapezoid ABCD, and in the second question we find out the area of this quadrilateral ABCD using two different methods. So we start with the first question. In the drawing we have a circle that is inscribed by trapezoid ABCD, or trapezoid ABCD blocks the circle. We know that side DA equals to 41 units in its length, side CB also equals to 41 units in its length, side AB equals to 50 units in its length. Again, our task is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is defined as a trapezoid. The two parallel bases, that is to say DC and AB, are defined as the bases of this trapezoid ABCD. So if we define the left of side, the base DC as A, and the left of the base AB as B, then the area of this trapezoid ABCD, will be equal to the sum of its two parallel bases, that is to say A plus B, times the height h over 2. The height h must create 90 degrees with the two parallel bases. Again, the area of this trapezoid is equal to the sum of its two parallel bases, that is to say A plus B, times the height h over 2. So first of all, we will define relevant points to this question with letters. We define the point of tendency of tangent DC with this circle. This point is point E. We define the point of tendency of tangent DA with this circle. This point is point F. We will define the point of tendency of tangent CB with this circle. This point is point G. And finally, we will define the point of tendency of tangent AB with this circle. This point is point H. Here we can implement rule 2. Repeat clicking on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle. This is the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. In our drawing, and focus on this common standpoint point D. From this common standpoint point D, we have two tangents to this circle, tangent DE and tangent DF. And according to rule 2, they are equal to each other. That is to say, DE equals to DF. So if we define the length of tangent DE as A, then the length of tangent DF must be also equal to A, because they are equal to each other according to rule 2. Likewise, we focus on this common standpoint point A. From this common standpoint point A, we have two tangents to this circle, tangent AF and tangent AH. And according to rule 2, they are equal to each other. That is to say AF equals to AH. So if we define the length of tangent AF as B, then the length of tangent AH must be also equal to B, because they are equal to each other according to rule 2. Likewise, we focus on this common standpoint point C. From this common standpoint point C, we have two tangents to this circle, tangent CE and tangent CG. And according to rule 2, they are equal to each other. That is to say, CE equals to CG. So if we define the length of tangent CE as C, then the length of tangent CD, the length of tangent CG must be also equal to C, because they are equal to each other according to rule 2. And finally, we focus on this common standpoint point B. From this common standpoint point B, we have two tangents to this circle, tangent BG and tangent BH. And according to rule 2, they are equal to each other. That is to say, BG equals to BH. So if we define the length of tangent BG as D, Then, the length of tangent BH must be equal to D according to rule 2. What is the value of side AB plus side CB? Side AD plus side CB. AD plus CB equals to A plus B plus C plus D. And again, we should find out that side AD plus the opposite side CB, trapezoid ABCD, equals to A plus B plus C plus D. Likewise, what is the value of side DC of the trapezoid ABCD plus the opposite side AB? DC plus AB so DC plus AB equals to A plus B plus C plus D. So she found out that those two expressions, they are both equal to A plus B plus C plus D, and therefore they are equal to each other. That is to say, AD plus CB equals to DC plus AB. So, now we found out that AD plus CB equals to DC plus AB. AD is 41 plus CB. CB is also 41, and it is equals to DC. DC is the missing side, so we'll leave it as it is, plus AB. AB equals to 50 units in its length according to what's given us in the question. So in total we have found out that 41 plus 41 equals to DC plus 50. 41 plus 41 is 82, so 82 equals to DC plus 50. So here we subtract 50 from this equation, and finally we get that the missing side DC is equal to 82 minus 50 is 32. So the missing side DC equals to 32 units in its length. So actually, this is the missing side DC is equals to 32 units in its length. In the next step, we will do a construction, that is to say, from this point C, we will do a perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AB. This point is point J. Likewise, we will do another construction, that is to say, from point D, we will do a perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. ABCD is a trapezoid, and a trapezoid is a quadrilateral with one pair of parallel sides. So in trapezoid ABCD, side DC is parallel to side AB. Those two angles, they are both defined as one-sided interior angles, and they are located between the parallel lines DC and AB. And therefore, according to Rule 17, the sum of those two one-sided interior angles is equal to 180 degrees. And again, on Rule 17, according to Rule 17, the sum of one-sided interior angles that are located between two parallel lines is equal to 180 degrees. In the moment, we have line A that is parallel to line B. This is the red line C that cuts the two parallel lines at those 2 points. In addition, we have those two angles alpha and beta that are defined as one-sided interior angles. And according to this rule, Rule 17, because of the fact that those two one-sided interior angles alpha and beta are located between the parallel lines A and B, the sum of those two one-sided interior angles must be equal to 180 degrees. So alpha plus beta equals to 180 degrees according to this rule, Rule 17. So we can actually implement Rule 17 in our drawing. Why? Because in our drawing, those two one-sided interior angles are located between the parallel lines DC and AB. And therefore, according to Rule 17, the sum of those two one-sided interior angles must be equal to 180 degrees. This is a right angle, that is to say it is equal to 90 degrees in its size, plus this missing angle, that is actually angle DCJ. In total, the sum of those two one-sided interior angles must be equal to 180 degrees according to Rule 17. Repeat again, if we found out that 90 degrees plus the missing angle DCJ in total must be equal to 180 degrees because of the fact that those two one-sided interior angles are located between the parallel lines DC and AB. Here we subtract 90 degrees from this equation and we get that the missing angle DCJ is equal to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle DCJ that is equal to 90 degrees in its size according to Rule 17. Likewise, those two one-sided interior angles, they are both located between the same parallel lines, that is to say DC and AB, and therefore according to Rule 17, the sum of those two one-sided interior angles must be equal to 180 degrees. This is a right angle, that is to say it is equal to 90 degrees in its size. So 90 degrees plus the size of this missing angle, that is actually angle CDN. In total, the sum of those two one-sided interior angles must be equal to 180 degrees in its size. And again, 90 degrees plus the missing angle CDN in total must be equal to 180 degrees according to the same rule, Rule 17. Here we subtract 90 degrees from this equation and finally get that the missing angle CDN is equal to 180 degrees minus 90 degrees is 90 degrees. So the missing angle CDN equals to 90 degrees in its size. This is the missing angle CDN that is equal to 90 degrees in its size according to Rule 17. So in the big quadrilateral DCJN, we have 1, 2, 3, 4 right angles. Therefore, according to Rule 5, quadrilateral DCNG is a right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DCJN, side DC must be equal to the opposite side NJ, but DC is 32, therefore the opposite side NJ must be also equal to 32 units in its length. Likewise, according to the sum rule, in the sum arterial DCJN, side CJ must be equal to the opposite side DN. So, let it down if you found out that side CJ must be equal to the opposite side DN. In the next step, we focus on those two right triangles. This is the right triangle DNA, and this is the right triangle CJB. On those two right triangles, those two sides are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. Those two sides, they are both equal to 41, therefore they are equal to each other. And finally, those two sides are also equal to each other. So in the next step, I'll prove that those two sides, that is to say, AN equals to JB. So I copied those two right triangles in a new page and I proved that those two sides are equal to each other. That is to say, side AN equals to side JB. So actually, those are the two right triangles that I copied from the original domain. This is the right triangle DNA. This is the right triangle CJB. The hypotenuses of those two right triangles are both equal to 41. So I defined that both of them are equal to y. Those two sides are also equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. So if side DN equals to x, then side CJ must be also equal to x. Those are the two sides that we have to prove that those two sides are equal to each other. That is to say, AN equals to JB. Why AN equals to JB? First of all, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle DNA, y squared, that is the square of the hypotenuse, equals to x squared plus AN squared. Again, y squared equals to x squared plus AN squared. Here we subtract x squared from this equation and we get that AN squared equals to y squared minus x squared. Here we take a root out of this equation and finally get that the missing side AN equals to the square root of y squared minus x squared. AN equals to the square root of y squared minus x squared. Likewise, in this right triangle CJB, according to the Pythagoras theorem, y squared, that is the square of the hypotenuse, equals to x squared plus JB squared. Repeat again. Y squared equals to x squared plus JB squared. Here we subtract x squared from this equation and finally get that JB squared equals to y squared minus x squared. Here we took a root out of this equation and finally found out that the length of side JB is equals to the square root of y squared minus x squared. And because of the fact that those two, both sides, they are both equal to the square root of y squared minus x squared, they are equal to each other. That is to say, AN equals to JB. So if we found out that AN equals to JB, so if we define the length of side AN as x, then the length of side JB must be also equal to x because they are equal to each other. AB, from one side it is equal to 50 units in its length, but from the other side, AB consists of three line segments, AN, J, and J, and JB. So AN in total equals to x plus 32 plus x. Okay, again, from one side AB equals to 50 units in its length, we only told this given in question, but from the other side AB also equals to x plus 32 plus x. So for this equation we derive that 50 equals to x plus x is 2x plus 32. So 30 equals to 2x plus 32. Here we subtract 32 from this equation. And finally we get that 2x equals to 50 minus 32 is 18. So 2x equals to 18. Here we divide this equation by 2. And finally, we get that x equals to 18 over 2. 18 over 2 is 9. So actually, this is side JB, this equals to x, and x equals to 9. That is to say, JB equals to 9 units in its length. In the next step, I'll copy the right triangle CJB in a new page, and we will implement the Pythagoras theorem on this right triangle CJB. Here by PT is the abbreviation for Pythagoras theorem. The hypotenuse CB equals to 41 units in its length, and JB equals to 9 units in its length. CJ is the missing side. So actually, this is the right triangle CJB, that is according to the original theorem. In this right triangle CJB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. So I write it down. CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared. That is 1681, and it is equal to CJ squared. CJ is the missing side, so leave it as it is. So it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total, we found out that 1681 equals to CJ squared plus 81. Here we will subtract 81 from this equation, and finally get that 1681 minus 81 is 1600 equals to CJ squared. Here we take a root out of this equation, and finally we get that the missing side CJ equals to the square root of 1600, that is 40. So if we found out that this is the missing side CJ is equals to 40 units in its length. CJ is the height of trapezoid ABCD. Why CJ is the height? Because it creates 90 degrees with the base DC and with the base AB. Our test is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? According to the formula that I presented to you in the beginning of the lecture, the area of trapezoid ABCD must be equal to the sum of its two parallel sides, that is to say DC plus AB, times the height, that is CJ over 2. And again, if you found out that the area of trapezoid ABCD, that is the area that we are looking for in this question, it is equals to the sum of its two parallel sides, that is to say DC plus AB, times the height CJ over 2. DC is 32, plus AB is 50, according to what is given in the question, times CJ. We just right now found out that CJ equals to 40 units in its length, divided by 2. So in total, we found out that the area of this trapezoid ABCD that is the area that we are looking for in this question, is equal to 32 plus 50 times 40 over 2. 32 plus 50 is 82, and 40 over 2 is 20. So in total, the area of trapezoid ABCD equals to 82 times 20. 82 times 20 is 1640 square units in its size. Then that is the answer to the first question. And again, we should find out that the area of this trapezoid ABCD, that is the area that we are looking for in this question, is equal to 1640 square units in its size. So we finish the first question. In the next step, I'll present to you the second question, and we'll solve the second question by using two different methods. In the second question, our test is to find out the area of this quadrilateral ABCD. So in the drawing we have quadrilateral ABCD. This is side AB, that's equals to 10 units in itself. This is side DC. Actually, side DC equals to 25 units in its length. This is angle ABC, that is right angle. This is angle ADC, that is also right angle. This is angle BCD, that is equals to 45 degrees in its size. Again, our task is to find out the area of this quadrilateral ABCD. So first of all, we will do a construction. That is to say, from this point B, we will go perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point M. In the next step, we will do another construction. That is to say, from this point A, we will go perpendicular on BN. Again, from point A, we will go perpendicular on BN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BN. This point is point M. By doing this construction, we can get the quadrilateral AM and D. In quadrilateral AM and D, we have 2 free angles. The sum of free angles is 270 degrees, so 270 degrees plus the size of this 4 missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 missing angle must be equal to 90 degrees in its size. So in quadrilateral AM and D, we have 4 angles, and therefore, according to rule 5, quadrilateral AM and D is a rectangle. So, write it down. This is quadrilateral AM and D. This is a rectangle because it has 4 rectangles. We define the length of side AM as A. We know that the opposite sides of a rectangle are equal to each other. So rectangle AM and D, side AM must be equal to the opposite side DN. But AM is 8, therefore the opposite side DN must be also equal to A units in its length. What is the length of this missing line segment and missing line segment NC? NC equals to DC minus DN. So now if you found out that NC equals to DC minus DN. So NC in total equals to DC is 25 according to what is given in the question, minus DN. DN is A. So in total NC equals to 25 minus A units in its length. This is line segment NC that is equals to 25 minus A units in its length. In the next step, we'll focus on this right triangle B and C. In this right triangle B and C, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. We continue to focus on this right triangle B and C. We have the rule that says that in front of equal angles in the triangle, there are equal sides. I repeat again, in front of equal angles in the triangle, there are equal sides. So in the right triangle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side ANC equals to 25 minus A, therefore side BN must be also equal to 25 minus A units in its length. So here, this is side BN. This is equals to 25 minus A units in its length. The big angle ABC equals to 90 degrees in its size, according to what is given in the question. This is the small angle NBC, that equals to 45 degrees in its size. Therefore, this missing angle, angle ABM, must be equal to the big angle ABC minus the small angle NBM. That is to say, it must be equal to the big angle ABC, that is 90 degrees, minus the small angle NBC, that is 45 degrees. 90 degrees minus 45 degrees is 45 degrees. Therefore, the size of the missing angle ABM equals to 45 degrees. We'll focus on the small right triangle ABM. The small right triangle ABM, this angle equals to 45 degrees. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We continue to focus on this right small triangle ABM. In right small triangle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side AM is A, therefore side BM must be also equal to A units in its length. So AM equals to A. What is the length of this missing line segment? Line segment MN. From the drawing, it is very easy to see that MN in total equals to BN minus BM. So it is known MN equals to BN minus BM. So MN equals to BN. BN is 25 minus A minus BM. BM is A. So in total, MN equals to 25 minus A minus A, that is 25 minus 2A. MN equals to 25 minus 2A units in its length. We know that the opposite sides of a rectangle are equal to each other. So in a rectangle AM and D, side MN must be equal to the opposite side AD. But MN is 25 minus 2A, therefore the opposite side AD must be also equal to 25 minus 2A units in its length. This is quadrilateral AB and D. Quadrilateral AB and D is a trapezoid. Why quadrilateral AB and D is a trapezoid? Because side BN is parallel to the opposite side AD. Why side BN is parallel to the opposite side AD? First of all, we know that the opposite sides of a rectangle are parallel to each other. So in rectangle AMND, side MN is parallel to the opposite side AD. But BN is a straight line. Why BN is a straight line? Because of the fact that angle BMN, this is angle BMN, this is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So therefore BN is a straight line. BN is a straight line, but MN is part of the straight line BN. Again, MN is part of the straight line BN and is parallel to AD. If a part of the straight line is parallel to another straight line, then the straight line BN itself must be also parallel to the straight line AD, to the other straight line AD. So because of the fact that in quadrilateral A, B, and D, side BN is parallel to the opposite side AD, quadrilateral A, B, and D is a trapezoid. So if you know, if you found out that quadrilateral A, B, and D is a trapezoid, because it has one pair of parallel sides. That is to say, BN is parallel to AD. Quadrilateral A, B, and D is a trapezoid. And again, quadrilateral A, B, and D is a trapezoid because it has one pair of parallel sides. What is the area of this quadrilateral? Quadrilateral A, B, and D. What is the area of trapezoid A, B, and D? Because quadrilateral A, B, and D is a trapezoid. So, what is the area of trapezoid A, B, and D? According to the formula that I presented to you in the beginning of the lecture, the area of trapezoid A, B, and D must be equal to the sum of its two parallel sides, that is to say BN plus AD, times the height AM. Why AM is the height? Because it creates 90 degrees with the two parallel bases. So times the height AM over 2. And again, if you found out that the area of this trapezoid A, B, and D, in total it is equal to the sum of its two parallel sides, that is to say BN plus AD, times the height AM over 2. BN is 25 minus A, plus AD. AD is 25 minus 2A, times the height AM. AM is A over 2. So in total, if you found out the area of this trapezoid A, B, and D, in total it is equal to 25 minus A plus 25 minus 2A times A over 2. 25 plus 25 is 50. Minus A minus 2A is minus 3A times A over 2. So if we found out that the area of trapezoid A, B, and D equals to 50 minus 3A times A over 2. Here we'll open the brackets and get that 50 minus A is 50A, minus 3A times A is minus 3A squared over 2. So total we found out that the area of this trapezoid A, B, and D equals to 50A minus 3A squared over 2 square units. In the next step, we will implement the Pythagoras theorem on this small right triangle ABM. So I copy this small right triangle ABM in a new page and we will implement on it the Pythagoras theorem. The hypotenuse AB equals to 10 units in its length, according to what is given as the question. Side AM equals to A, and side BM also equals to A. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle ABM, that is according to the original domain. In this right triangle ABM, according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, equals to BM squared plus AM squared. So write it down. AB squared, that is the square of the hypotenuse, equals to BM squared plus AM squared. AB is 10, therefore AB squared is 10 squared, that is 100. And it is equal to BM squared. BM is A, therefore BM squared is A squared plus AM squared. AM is also A, therefore AM squared is A squared. A squared plus A squared is 2A squared. So in total we found out that 100 equals to 2A squared, or 2A squared equals to 100. Our task is to find out the area of this quadrangle ABCD. So what is the area of quadrangle ABCD? From the domain it is very easy to see. To see that the area of this quadrangle ABCD in total equals to the area of this trapezoid A, B, and D plus the area of this right triangle B and C. So write it down. The area of this quadrangle ABCD equals to the area of trapezoid A, B, and D plus the area of this right triangle B and C. Again, we shall find out that the area of this quadrangle ABCD, that is the area that we're looking for in this question. In total, it is equal to the area of trapezoid A, B, and D plus the area of the right triangle B and C. We already found out that the area of trapezoid A, B, and D equals to 50A minus 3A squared over 2 plus the area of this right triangle B and C. The area of the right triangle B and C equals to the base NC times the height NB over 2. So again, we found out that the area of this right triangle B and C in total it is equal to the base NC times the height NB over 2. So in total, the area of quadrilateral ABCD equals to 50A minus 3A squared over 2 plus NC is 25 minus A times NB. NB is also 25 minus A, so it is 25 minus A squared divided by 2. So in total, we found out that there quadrilateral ABCD equals to 50A minus 3A squared plus 25 minus A squared over 2. So it is 50A minus 3A squared plus 25 minus A squared. 25 minus A squared equals to 25 squared, that is 625, plus A squared, minus 2 times 25 times A is minus 50A over 2. $58 minus 50A is 0, so those two expressions will get cancelled, and we're left only with minus 3A squared plus A squared is minus 2A squared plus 625. So in total, we have found out that the area of quadrilateral ABCD equals to 625 minus 2A squared over 2. But we have already found out that 2A squared equals 200. So we can substitute 2A squared in this expression by 100. We do it now, we get that the area of quadrilateral ABCD in total equals to 625 minus 2A squared. And 2A squared is 100 over 2. So in total, the area of quadrilateral ABCD equals to 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in size. That's it, answer to the question. Repeat again, we found out that the area of this quadrilateral ABCD, according to the first method, is equal to 262.5 square units in its size. So we finish with the first method. In the next step, I present to you how to find out the area of this quadrilateral ABCD according to the second method. In the second method, we will do a construction, that is to say, we'll extend side DA and side CB on this quadrilateral ABCD by side line until they touch each other. And we'll define their touching point, this point is point M. By doing this construction, you're going to do the big right triangle MDC. The big right triangle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We'll continue to focus on the big right triangle MDC. On the big right triangle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But DC is 25, therefore MD must be also equal to 25 units in its length. Side MC is the hypotenuse of this right triangle MDC. So MC is an hypotenuse, it is absolutely a straight line. So if you focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side, of a straight line is equal to 180 degrees. So which angles we have the left side of the straight line MC at point B? We have this angle which is equal to 90 degrees in size, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. The next step we'll focus on this small right triangle MBA. The small right triangle MBA, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We will continue to focus on the right small triangle MBA. On the right small triangle MBA, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side AB equals to 10, therefore side MB must be also equal to 10 units in its length. Our task is to find out the area of this quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the drawing, it is very easy to see that the area of this quadrilateral ABCD is equal to the area of the big right triangle MDC minus the area of this small right triangle ABM. Repeat again. The area of this quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of the small right triangle MBA. So write it down. The area of quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of the small right triangle MBA. Repeat again, the area of this quadrilateral ABCD. In total, it is equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base DC times the height MD over 2. And again, the area of the big right triangle MDC in total is equal to the base DC times the height MD over 2. Minus the area of this small right triangle MBA. The area of the small right triangle MBA equals to the base AB times the height MB over 2. And again, the area of this small right triangle MBA equals to the base AB times the height MB over 2. DC is 25, according to what is going to the question. DM is also 25. So in total, if you found out that the area of this big right triangle MDC is equal to 25 square over 2 minus the area of this small right triangle MBA. It is equal to AB, that is 10, minus MB, that is also 10 over 2. So the area of this small right triangle MBA equals to 10 square over 2. $25 square is 625, minus 10 square, this is 100, over 2. So in total, if you found out that the area of this quadrilateral ABCD is equal to 625 minus 100 over 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in its size. So luckily, in both methods, we found out luckily that the area of this quadrilateral ABCD, this is the area that we are looking for in this question, is equal to 262.5 square units in its size. So we finish with the second method of the second question. The next step, as soon as the lecture, we'll start with the first question, of course. In the first question, our task is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD, and because of the fact that side DC is parallel to the opposite side AB, this quadrilateral ABCD is defined as a trapezoid because it has one pair of parallel sides. The two parallel sides, that is to say DC and AB, are defined as the bases of this trapezoid ABCD. So if we define the length of side the base BC as A and the length of the base AB as B, then the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is to say A plus B times the height edge over 2. The height edge must raise 90 degrees with the two parallel bases. So a trapezoid is a quadrilateral with one pair of parallel sides, and the area of the trapezoid is equal to the sum of its two parallel sides times the height over 2. So in the drawing, we have a circle that is inscribed by trapezoid ABCD. Trapezoid ABCD blocks this circle. In addition, we know that side DA equals to 41 units in its length, side CB also equals to 41 units in its length, and side AB equals to 50 units in its length. Our test is to find out the area of this trapezoid ABCD. So first of all, we defined the relevant points to this question with letters. We define the point of tendency of tangent DC with this circle, this point is point E. We define the point of tendency of tangent DA with this circle, this point is point F. We define the point of tendency of tangent CB with this circle, this point is point G. And finally, we define the point of tendency of tangent AB with this circle, this point is point H. The next step, we implemented rule 2 in our drawing. Let's click on rule 2. According to rule 2, the lengths of two tangents from a common exam point to a circle are equal. In the drawing, we have a circle. This is the common exam point P. From this common exam point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. What is in our drawing? If we focus on this common exam point D, from this common exam point D, we have two tangents to this circle, tangent DE and tangent DF. And according to rule 2, they are equal to each other. That is to say, DE equals to DF. So if we define the length of tangent DE as A, then the length of tangent DF must be also equal to A because they are equal to each other according to rule 2. Likewise, if we focus on this common exam point C, from this common exam point C, we have two tangents to this circle, tangent CE and tangent CG. And according to rule 2, they are equal to each other. That is to say, CE equals to CG. So if we define the length of tangent CE as C, then the length of tangent CG must be also equal to C because they are equal to each other according to rule 2. Likewise, we focus on this common standpoint, point A. From this common standpoint, point A, we have two tangents to this angle, tangent AF and tangent AH. And according to rule 2, they are equal to each other. That is to say, AF equals to AH. So if you define the length of tangent AF as B, then the length of tangent AH must be also equal to B because they are equal to each other according to rule 2. And finally, if we focus on this common standpoint, point B, from this common standpoint, point B, we have two tangents to this angle, tangent BG and tangent BH. And according to rule 2, they are equal to each other. So if we define the length of tangent BG as D, then the length of tangent BH, the length of tangent BH must be also equal to D because they are equal to each other according to rule 2. What is the length of side AD plus the opposite side CB? From the drawing, it is very easy to see that AD plus CB in total equals to A plus B plus C plus D. And again, side AD plus the opposite side CB in trapezoid ABCD in total equals to A plus B plus C plus D. Likewise, what is the length of side DC plus the opposite side AB? DC plus AB in total equals to A plus B plus C plus D. So if you found out that side DC plus the opposite side AB also equals to A plus B plus C plus D. And because of the fact that those two expressions are both equal to A plus B plus C plus D, it means that they are equal to each other. That is to say, AD plus CB equals to DC plus AB. Again, AD plus CB equals to DC plus AB. AD is 41, CB is also 41, DC is the missing side, so 50 cities, and AB is 50. 41 plus 41 is 82, equals to DC plus 50. If subtract 50 from this equation, if I found out that the missing side DC equals to 82 minus 50 is 32. So this is the missing side DC, that is equals to 32 units in its length. In the next step, we did the construction, that is to say, from this point C, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. And in the next step, we did another construction, that is to say, from point D, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. Note that ABCD is a trapezoid. In trapezoid ABCD, side DC is parallel to side AB. Those two angles are defined as one-sided interangles and are located between the parallel lines DC and AB. And therefore, according to rule 17, the sum of those two one-sided interangles is equal to 180 degrees. This is a right angle, that is to say it is equal to 90 degrees in size, plus this missing angle, that is option angle DCJ. In total, the sum of those two one-sided interangles must be equal to 180 degrees according to rule 17. And again, if you found out that 90 degrees plus the missing angle DCJ, in total, they must be equal to 180 degrees according to rule 17. Here, we subtract the 90 degrees from the equation, and find out that the missing angle DCJ equals to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle DCJ, that is equal to 90 degrees in its size. Likewise, those two angles are also defined as one-sided interangles and are located between the same parallel lines DC and AB. And therefore, the sum of those two one-sided interangles must be equal to 180 degrees according to rule 17. This is a right angle plus this missing angle, that is angle CDN. In total, they must be equal to 180 degrees according to rule 17. Repeat again. 90 degrees plus the missing angle CDN. In total, they must be equal to 180 degrees according to rule 17. Here, we subtract the 90 degrees from the equation, and finally found out that the missing angle CDN equals to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle CDN. It is equals to 90 degrees in size. So in quadrilateral there are DCJN where 1, 2, 3, 4 right angles. And therefore quadrilateral DCJN is a right angle because it has 4 right angles. So we know that the opposite sides of a right angle are equal to each other. So in right angle DCJN, side DC must be equal to the opposite side JL. But DC is 32, therefore the opposite side JL must be also equal to 32 units in its length. Likewise, according to the sum rule, in the sum of the DCJN, side DL must be equal to the opposite side CJ. So those two sides must be equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. In the next step, we focus on those two right angles. This is the right angle DNA, and this is the right angle CJB. We should prove that those two right angles can go to each other according to side rule. That is to say, those two sides are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. Those two sides are both equal to 41 units and therefore they are equal to each other. And finally, I proved that those two sides are also equal to each other. I copied those two right angles in a new page and I proved that those two sides are equal to each other. And finally, those are the two right angles that are copied from the original drawing. Those two sides are both equal to 41 units and therefore they are equal to each other. So if we define side DA as y, then side CB must be also equal to y, because they are equal to each other. Likewise, those two sides are also equal to each other, according to the rule that the opposite sides of a rectangle are equal to each other. So if we define the length of side DN as x, then the length of side CJ must be also equal to x. Now we have to prove that those two sides are equal to each other. Why those two sides are equal to each other? We implemented the Pythagoras theorem on this right triangle. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle DNA, y squared, that is the square of the hypotenuse, equals to x squared plus an squared. Repeat again, y squared equals to x squared plus an squared. Here we subtracted x squared from this equation, and finally found out that an equals to an squared equals to y squared minus x squared. Here we took out of this equation and finally found out that an equals to the square root of y squared minus x squared. This is side an, that equals to the square root of y squared minus x squared according to the Pythagoras theorem. Likewise, we implemented the Pythagoras theorem on this right triangle CJB. The right triangle CJB, according to the Pythagoras theorem, y squared equals to x squared plus jb squared. Again, y squared equals to x squared plus jb squared. Here we subtracted x squared from this equation and finally found out that y squared minus x squared equals to jb squared. Here we took out of this equation and finally found out that the density inside jb equals to the square root of y squared minus x squared. And because of the fact that those two sides are both equal to the square root of y squared minus x squared, they must be equal to each other. That is to say, an equals to jb. So this is side AN, that equals to side JB. So if we define the length of side AN as x, then side JB must be also equal to x. AB from one side equals to 50 units in its length, according to what is given us the question. But from the other side, AB also equals to x plus 32. So again, we found out that from one side AB equals to 50 units in its length, but from the other side it is also equals to x plus 32. X plus x is 2x, so on this side of the equation we have 2x plus 32. On the other side of the equation we have 50. 50 equals to 2x plus 32. Here we subtract the 32 from this equation, if I found out that 2x equals to 50 minus 32 is 18, so 2x equals to 18. Here we divided this equation by 2 and I found out that x equals to 9 units in its length. Okay, this is inside JB, this equals to x, and x equals to 9 units in its length. It means that JB equals to 9 units in its length. In the next step, I copied the right triangle CJB in a page and implemented the Pythagoras theorem on this right triangle CJB. So okay, this is the right triangle CJB that comes from the original drawing. This right triangle CJB, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 1681 and it is equal to Cj square. Cj is the missing side, so electricity, so it is Cj square plus Jb square. Jb is 9, therefore Jb square is 9 square, that is 81. So in total we have found that 1681 equals to Cj square plus 81. Here we subtracted 81 from this equation, we found out that 1681 minus 81 is 1600, so 1600 equals to Cj square. Here we took root out of this equation, and we found out that Cj equals to the square root of 1600, this is 40. So this is side Cj, this is equals to 40 units in there. Cj is also the height of trapezoid ABCD, right? Because it has 90 degrees with the two bases, with the two parallel bases. Our test is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? According to the formula that I presented to you at the beginning of the lecture, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say DC plus AB times the height Cj over 2. Okay, again, the area of this trapezoid ABCD is equal to the sum of its two parallel bases, that is actually DC plus AB times the height Cj over 2. DC is 32, AB is 50, Cj is 40 over 2. 32 plus 50 is 82, 40 over 2 is 20. So in total, the area of trapezoid ABCD equals to 82 times 20. 82 times 20. 82 times 20 is 1640 square units in size. So we found out that the area of this trapezoid ABCD, that is the area that we are looking for in this question, it is equal to 1640 square units in size. So we finished with the first question. The next step I presented to you the second question, and we solved the second question by using two different methods. Our task in the first and the second question is to find out the area of this quadrilateral ABCD. So in the moment we have quadrilateral ABCD. This is side AB, this is equals to 10 units in its length. This is side DC, this is equals to 25 units in its length. This is angle ABC, that is right angle. This is angle ADC, that is also right angle. This is angle BCD, this is equals to 45 degrees in its size. Again, our test is to find out the area of this quadrilateral ABCD. So first of all, we did the construction, that is to say from point B we go perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and side DC. This point is point M. In the next step, we did another construction, that is to say from point A we go perpendicular on BN. Again, from point A we go perpendicular on BN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BN. This point is point M. By doing these constructions, if we can do quadrilateral AM and D. In quadrilateral AM and D, we have 1, 2, 3 degrees. The sum of 3 degrees is 270 degrees, so 270 degrees plus the size of this fourth missing angle, total must be equal to 360 degrees. According to the rule, the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral AM and D, we have 4 degrees. In quadrilateral AM and D, we have 4 degrees. And therefore, quadrilateral AM and D is a rectangle. We define the left of side AM as A. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AM and D, side AM equals to the opposite side DN. But AM is A, therefore the opposite side DN must be also equal to A units in its length. What is the length of this missing line segment NC? NC equals to DC minus DN. Again, NC equals to DC minus DN. So NC equals to DC, that is 25, minus DN, that is 8. So in total, NC equals to 25 minus A units in its length. This right angle BNC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We have also the rule that in front of equal angles in the triangle there are equal sides. We focus on the right angle BNC. On the right angle BNC, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side NC is 25 on the side, therefore side BN must be also equal to 25 minus 5 units in its length. Okay. we have this is angle ABC, that is a right angle. The small angle NBC equals to 45 degrees in its size. So the big angle ABC minus the small angle NBC is the value of this missing angle ABM. Therefore, the value of the missing angle ABM must be equal to 90 degrees minus 45 degrees, that is 45 degrees. So in this full right triangle ABM, this angle equals to 45 degrees. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the small right triangle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side AM equals to A, therefore side BM must be also equal to A units in its length. What is the length of MN? MN equals to BN minus BM. And again, MN equals to BN minus BM. So MN equals to BN, that is 25 minus A, minus BM, that is A. So in total, MN equals to 25 minus A minus A, that is 25 minus 2A. In rectangle AM and D, the opposite sides are equal to each other. That is to say, AMN equals to AD. But MN is 25 minus 2A, therefore AD must be also equal to 25 minus 2A units in its length. This is quadrangle AB and D. Quadrangle AB and D is a trapezoid. Why quadrangle AB and D is a trapezoid? First of all, we'll focus on this rectangle AM and D. We know that the opposite sides of a rectangle are parallel to each other. So in rectangle AM and D, side MN is parallel to the opposite side AD. BN is a straight line. Why BN is a straight line? Because this is angle BMN. That is equal to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, BN is a straight line. MN is part of the straight line BN. Again, MN is part of the straight line BN. MN is parallel to AD. According to the rule, the opposite sides of a rectangle are parallel to each other. So if a part of the straight line is parallel to another straight line, then the straight line BN itself must be also parallel to the other straight line AD. So in quadrangle AB and D, side BN is parallel to the opposite side AD. And therefore quadrangle AB and D is a trapezoid because it has one pair of parallel sides. Again, if you found out that in total that quadrangle AB and D is a trapezoid. But what is the area of this trapezoid? Trapezoid AB and D. According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid AB and D must be equal to the sum of its two parallel sides, that is to say BN plus AD times the height AM over 2. So again, the area of trapezoid AB and D equals to the sum of its two parallel sides, that is actually BN plus AD times the height AM over 2. BN is 25 minus A, BN is 25 minus A, plus AD. AD is 25 minus 2A. Again, BN is 25 minus A, and AD is 25 minus 2A. AM is A. AM is A. Divided by 2. So in total, we found out that the area of trapezoid AB and D equals to 25 minus A plus 25 minus 2A times A over 2. 25 plus 25 is 50, and minus A minus 2A is minus 3A multiplied by A over 2. 50 times A is 50A, minus 3A times A is minus 3A squared over 2. So in total, we found out that the area of this trapezoid AB and D equals to 58 minus 3A squared over 2. In the next step, I copied the small right triangle ABM in a new page and we implemented the Pythagoras theorem on this small right triangle ABM. This is the small right triangle ABM that I copied from the original drawing. In this small right triangle ABM, according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. AB is 10, therefore B squared is 10 squared, that is 100, and it is equals to BM squared. BM is A, therefore BM squared is A squared, plus AM squared. AM is also A, therefore AM squared is A squared. So in total, 100 equals to A squared plus A squared, that is 2A squared. So we found out that 2A squared equals to 100. Our task is to find out the area of this quadrangle ABCD. So what is the area of quadrilateral ABCD? From the drawing it is very easy to see that the area of this quadrilateral ABCD equals to the area of trapezoid A, B, and D plus the area of this right triangle B and C. Okay, again, the area of this quadrilateral ABCD, that is the area that we're looking for this question, is equal to the area of trapezoid A, B, and D plus the area of the right triangle B and C. We have already found out that the area of trapezoid A, B, and D equals to 50A minus 3A squared over 2 plus the area of the right triangle B and C. What is the area of the right triangle B and C? Is equals to the base and C times the height and B over 2. And again, the area of the right triangle B and C equals to the base and C times the height and B over 2. So the area of quadrilateral A, B, C, D in total equals to 3A squared minus 50A minus 3A squared over 2. And C is 25 minus A times Bn. Bn is also 25 minus A. So total NC times Bn is 25 minus A squared. Again, NC times Bn is 25 minus A squared. So in total, the area of quadrilateral ABCD equals to 50A minus 3A squared plus 25 minus A squared over 2. So it is 50A minus 3A squared plus 25 minus A squared. 25 minus A squared equals to 25 squared, that is 625, plus A squared, plus 2 times 25 times 8, that is minus 50A. 50A minus 50A is 0, so we're left only with 625 plus 2A squared over 2. But we already found out that 2A squared equals 200, so we can substitute 2A squared in this expression by 100. We did it, and we found out that the area of quadrilateral ABCD equals to 625 minus 2A squared. Minus 2A squared is minus 100 over 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in size. So total, we found out that according to the first method, the area of this trapezoid ABCD, that is the area that we are looking for in this question, it is equal to 262.5 square units in size. So we finished with the first method. In the next step, I presented you how to find out the area of this trapezoid, the area of this quadrilateral ABC, the area of this quadrilateral ABCD according to the second method. In the second method, we did a construction, that is to say, we extended side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. This is their touching point. We define their touching point as point M. By doing this construction, we can here write big triangle MDC. Write big triangle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third angle must be equal to 45 degrees in size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We have the rule that in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But DC is 25, therefore the M must be also equal to 25 units in its length. MC is the opposite of this straight line MDC. So MC is an hypotenuse, it is absolutely a straight line. So if we focus on the left side of the straight line MC, if we focus on the left side of the straight line MC at point B, if the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line MC at point B? We have this angle that is right angle plus this missing angle. Total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the small right triangle MBA, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the small right triangle MBA, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side AB is equal to 10 units, and therefore side MB must be also equal to 10 units in its length. What is the area of this quadrilateral ABCD? The area of this quadrilateral ABCD is equal to the area of the big right triangle MDC minus the area of this small right triangle MBA. And again, the area of this quadrilateral ABCD in total is equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base DC times the height DM over 2. And again, the area of the big right triangle MDC in total is equal to the base DC times the height the m over 2. Minus the area of this forward line MBA. The area of this forward line MBA equals to the base AB times the height MB over 2. The area of this forward line MBA equals to the base AB times the height MB over 2. DC is 25, MD is also 25, AB is 10, and MB is 10. So in total, the area of quadrilateral ABCD equals to 25 squared, that is 625, minus 10 squared, that is 100 over 2. 625 minus 100 is 525. 525 over 2 is 262.5 square units in size. So in both methods, we should find out that the area of this quadrilateral ABCD, that is the area that we are looking for this question, it is equal to 262.5 square units in its size. Okay, thank you very much.